New pictures captured by the James Webb Space Telescope have staggered specialists. Rather than merely expanding our understanding of the universe, these photographs have uncovered an unsettling reality. Our perpetual consciousness is insufficient to fully grasp the potential consequences of the universe in its early stages. The theory of the Big Bang seems to be reaching its limits, prompting us to consider new hypotheses about its origins. The question arises: how is the universe formed, and why does this new discovery challenge even the most experienced specialists to understand more about the Big Bang and the intricate details of this revelation? What if we examine the possibility of the Big Bang itself defying conventional thinking? The Big Bang was not an explosion in pre-existing space. Perhaps it was space itself that began around 13.8 billion years ago, along with matter and time. A phenomenon in physics and cosmology describes points where gravity is so intense that the curvature of space-time becomes infinite. Today, billions of years after the universe's inception, we see that our immense home is part of a grand cycle. For specialists, this represents a crucial piece of the universe's puzzle, as its very existence is clearly part of an eternal process. However, it is essential to understand that the universe is not expanding into pre-existing space. Rather, space itself is constantly increasing in size. According to current theories, the first stars began to shine somewhere between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Ages. This was the point when the first luminous celestial objects merged to form mature systems. However, the speed with which these vast systems formed remains a baffling mystery. An abundance of information emerged through the first images captured by the James Webb Space Telescope in July 2022. Specialists revealed that the telescope had detected remarkable galactic systems, some of which had already existed around 300 million years after the universe's formation. Unlike the vast, permanent structures formed much later, these early galaxies were significantly smaller and less massive. This aligns with the scientific model accepted by specialists. The density of matter in the early universe was simply not sufficient to create galaxies the size of those observed today. Initially, what began as the identification of 6 glowing, red-shifted spots by the James Webb Telescope ended up sparking one of the most significant cosmological mysteries of recent years. Although these newfound galaxies are similar in age to more recently documented ones, they are nearly as expansive as our own Milky Way. This has created a fascinating mystery. After analyzing a series of images captured by the telescope's near-infrared camera, specialists identified the aforementioned light sources, using redshift to confirm that the light from these objects took over 1 billion years to reach our eyes on Earth. Thus, we are dealing with structures that existed roughly 570 million years after the Big Bang. By examining the characteristics of these systems, it was concluded that the telescope had captured 6 early galaxies in its photographs. Amazingly, these galaxies were so massive that they challenged conventional cosmological theories. Instead of the expected smaller galaxies, structures were identified that were nearly as wide as our Milky Way, despite having formed very early in the universe's history. If we continue to analyze the data gathered by the James Webb Telescope, this gravitationally bound cluster of stars already contained more than 10 billion times the mass of the Sun at that time, with one galaxy possibly exceeding 10 billion solar masses. However, whether this scenario is accepted, the mystery remains unresolved. For instance, there would have been significantly more stellar mass in the early universe than previously expected, presenting a problem. The identified objects challenge nearly all conventional cosmological theories. If even one of these massive systems is confirmed as real, it would overturn prior assumptions. Moreover, the density of matter in the early universe would need to be several times greater than previously predicted to account for this phenomenon. Another similarly strange explanation depends on how these massive systems formed, which remains entirely unknown. These discoveries and the debates surrounding the Big Bang have led some researchers to diverge from this hypothesis. Various astrophysicists with alternative viewpoints feel their perspectives are not being adequately represented in scientific journals. Even those who express doubts about existing theories are often labeled as unreasonable. However, it is clear that even specialists who still support the Big Bang theory are constantly confronted with questions that lack convincing answers. These inquiries include specific issues such as, why and how did something arise from nothing 13.8 billion years ago? Could something have started from nothing? Or was there some triggering event? Or was it all an accident? Steven Weinberg pointed out that the concept of time, as we understand it, began only with the Big Bang. Therefore, this process could not have been triggered by something external to it. Similarly, a puzzling question relates to the uniformity of radiation and density throughout the universe. Regardless of which direction or distance we observe, on a larger scale, we find similar densities and distributions of galaxies, nebulae, and radiation everywhere. Conventional explanations resolve this inconsistency through the theory of cosmic inflation. However, some specialists take this assumption further, suggesting a theory of eternal inflation. According to this idea, inflation has only ceased in specific regions, like bubbles, and continues indefinitely elsewhere. This suggests that multiple universes could be forming in these bubbles, each with its unique physical laws. In this model, a key question arises: what if our universe does not represent the whole picture? More intriguingly, what if another universe existed before our own? In this case, the Big Bang would be part of a larger cycle. According to this view, our universe is part of a greater multiverse. Within this framework, the possibility of an eternal cycle of decay and renewal of universes is proposed. However, this is not the only perspective presented in the field of cosmology. For instance, in 1955, an article in NASA Space Times argued that there may never have been a Big Bang, proposing instead that the universe has existed for an infinite amount of time. In this view, the expansion of the universe would be non-existent, and the observed arrangement of matter could give the illusion of steady evolution. Additionally, another intriguing hypothesis arises from the realm of quantum physics and string theory. Some experiments have suggested that our universe, and everything within it, might simply be a flat, three-dimensional image projected onto a surface. This leads to the speculative idea that our reality might be the result of a higher-level simulation. While this might sound like the plot of an unconventional science fiction film, it could have connections to the Kardashev scale, a framework that measures the advancement of civilizations based on their ability to harness energy. If a Type 3 civilization were capable of fully harnessing the energy of an entire universe, it could, in theory, create a vast simulation with astonishing accuracy. Understanding the implications of such a scenario is an immensely complex task. Exploring the depths of cosmology and the origins of our universe takes us into a domain of profound mystery and ongoing scientific inquiry. The discoveries made by the James Webb Space Telescope have reignited discussions about the true nature of existence, challenging established theories and encouraging scientists to rethink fundamental aspects of cosmological understanding. At the heart of this inquiry lies the question of how things came to be, a cornerstone of modern cosmology. According to prevailing theories, about 13.8 billion years ago, the universe emerged from an extraordinarily dense and hot state, expanding rapidly and giving rise to space-time and matter as we know them today. This monumental event, often referred to as the Big Bang, was not simply an explosion within pre-existing space. Instead, it may have marked the very origin of space itself. The concept of a singularity, where gravitational forces are so intense that space-time becomes infinite, supports our understanding of this earliest stage of the universe. However, the discovery of early systems by the James Webb Space Telescope challenges assumptions about how quickly structures could have formed in the universe's infancy. These systems, detected within a few 100 million years of the Big Bang, appear remarkably developed and massive, defying expectations based on current cosmological models. One of the core issues raised by these findings is the nature of cosmic inflation. As proposed by the dominant theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand rapidly and uniformly. This rapid expansion would explain the consistency of the cosmic microwave background radiation observed throughout the universe. Yet, the new findings suggest complexities in the early evolution of the universe that may require modifications to inflationary models. The formation of galaxies like those seen by the James Webb Telescope challenges cosmologists to reevaluate the conditions and processes governing the universe's early development. These massive systems, immense in size and mass, suggest a matter density far exceeding previous estimates. The mystery deepens as scientists consider how such colossal structures could have formed and evolved in such a relatively short cosmic timespan. Moreover, the discovery of these early systems raises intriguing questions about the nature of dark matter and dark energy, two elusive components that comprise the majority of the universe's mass and energy. While dark matter is thought to provide the gravitational scaffolding for galaxies to form, and dark energy drives the accelerated expansion of the universe, their exact nature remains poorly understood. The James Webb Space Telescope's findings suggest that our current understanding of these phenomena may need to be reconsidered. Could there be unknown processes or interactions shaping the universe that we have yet to uncover? And if so, what implications might this have for our broader understanding of cosmology? As scientists continue to analyze the wealth of data provided by the James Webb Space Telescope, new theories are likely to emerge, potentially reshaping our understanding of the universe's origins, evolution, and ultimate fate. Each discovery brings us closer to unraveling the mysteries of existence while revealing how much we still have to learn.